Welcome back. This is the Tutor Wizard. I'm Adrian. Please subscribe right here. Hit the notification bell. We're doing Linear Algebra 1. Chapter 1 is Systems of Linear Equations. 1.7 is Gaussian Elimination in row echelon form. This lecture, what we're going to do is recap 1.7.3, solving linear systems using Gaussian elimination, and then we'll quickly talk about the rank and kronecker-capelli theorem about when we have inconsistent systems. Let's do that. For our first example, I'm not going to do all the details. I've written them out ahead of time. You have to practice shearing sheep. If you want to get to a row echelon form from a linear system, you need to augment the matrix, use Gaussian elimination, which is the 3 row operations in any order you want. As long as you use the 3 and use them correctly, you will get to an REF, which is unique up to whether you get leading ones or not, or the leading coefficient. Once I have REF, I can find out whether I have one solution, no solutions, or infinitely many. Remember, this process changed it, but it eventually gives us this equation and this equation are a simpler equivalent linear system. This system and this system now have the same solutions, and we can find, using back substitution, the solutions to this system much easier. This is one equation and 2 unknowns, therefore I'm going to let x3 be free. I solve for x2, and then I use back substitution to put x2 and x3 in this equation and solve for x1, and we write it in this form called the general solution, which is all the solutions to this system. In this case, because of the row of zeros, we got infinitely many solutions. To finish off, we're going to do the rank and kronecker-capelli theorem. What this tells us is whatever rank is, the theorem is going to say a system, whatever the size is, if it's linear, it's consistent, which means it has solutions, if and only if the rank of the coefficient matrix equals the rank of the augmented matrix. What? Break down what's happening. The rank of an augmented matrix, denoted rank A column B, is the way I'm going to write this. Mark Solomonovich likes to write it as rank of the augmented matrix equals the rank of the coefficient matrix, but this gets somewhat ambiguous. I like to just use rank and make it obvious so that our notation is clear. It's simply the number of leading entries and thus the number of non-zero rows in the REF of that augmented matrix. So therefore, when I ask this question, you can't tell yet. You have to put in the REF first, and then you answer the question. So here you can't tell. 2, 1, 2. You're like, well, how am I guessing? I already know because I cheated. I made the questions up. Similarly, the rank of the coefficient matrix. This is the coefficient matrix where we get rid of the equal sign now. We denote that rank A. And what the theorem is going to say is, in my notation, we're going to get that the rank of AB equals the rank of A if and only if the system is consistent. So if you have a linear system, the associated rank of the associated augmented matrix has to equal the rank of the coefficient matrix. Let's check and see why they suspect this first. It doesn't come out of a vacuum. Essentially, they start looking at systems. They're like, this seems to be a thing, and then they prove it. What is the rank of the following matrices? First of all, quickly, you've seen this. Watch the previous videos if you want to see how I did this. But an REF for this guy is 1, 1, 4, 0, 1, 1 half. An REF for this one is 1, 1, 4, 0, 0, 0. And an REF for this one is 1, 1, 4, 0, 0, 1. Therefore, we start looking at this. What is the rank of the augmented matrix? The rank is the number of non-zero rows, 2. So the rank of this matrix is, augmented matrix is 2. The rank of this one is number of non-zero rows. The rank is 1. And here is where we start getting into the theorem. The rank of this one is, I have 2 non-zero rows. But if it asks the second question, where now I have to squeeze this in, this now is 1, 1, 0, 1 is the coefficient matrix A. And here we have 1, 1, 0, 0, which is the coefficient matrix A. But here we have 1, 1, 0, 0 again. So what the theorem is saying is this now. What's the rank of this one? 1, 2. And this is 1, 2. So the ranks match of the coefficient matrix and the augmented matrix. They have the same rank, number of non-zero rows. And it had a solution, so it's consistent. Is this always the case? They seem to suspect this. And then they look at this. Well, this one had infinitely many. Well, if you look, though, the rank of the augmented matrix is 1, and the rank of the coefficient matrix is 1. So it matches, and it had solutions, infinitely many. But now here is where they say, it breaks. The rank of the augmented matrix is 1, 2. But the rank of the coefficient matrix is only 1. And so those ranks don't match, and this didn't have solutions. Is that a coincidence? No, it's if and only if is what they're going to say. Let's state the theorem. Okay, to end this video, we have the theorem, which is due to Kronecker and Capelli. Let S be an n by n linear system of equations. The statement is now S is consistent, which means it has at least one solution, if and only if the rank of the augmented matrix is equal to the rank of the coefficient matrix. Again, who are all these pieces? The augmented matrix is all the coefficients equals B, this guy, from the system. And the coefficient matrix is the matrix with just the coefficients standing in front of our variables, so this guy. Now if I look, we saw these in the previous video. This is just the recap. So in the last video we saw that this one was consistent and had a unique solution. 11 over 4, 17 over 4, 37 over 4, you can look. This one is inconsistent and has no solutions. What the theorem is now telling us is if you row reduce and then look at this and count, we get 1, 2, 3 is the rank of this augmented matrix. And then if you, I wrote it down for emphasis, but if you just use your hand and block off the last column, now that you have the coefficient matrix, what's the rank of this? Still 1, 2, 3. So it matches and it has to be consistent is what our theorem says. The way you're going to use the theorem actually is this case only. You want to say it's not consistent or has no solutions. The best way to do that is row reduce now. Now I should take that away for emphasis. What is the rank of the augmented matrix? 1, 2, 3. And this is where it gets it. This is the contradiction if you do it the other way. But now what the theorem is saying is what's the rank of the coefficient matrix? 1, 2. So the rank of A equals B, the augmented matrix, is 3, which does not equal 2, which is the rank of A. So no solutions is what you can argue. The theorem is trying to make your life easier, not torture you. So what they're trying to point out is if you want to say in the other two cases, when we say solve a linear system, we mean give the general solution. So if it's consistent, you have to explicitly backtrack and give me the solution of 11 over 4, 17 over 4, 37 over 4, whatever it is. Or if you have infinite solutions. But if you have an inconsistent system, you just want to say no solutions and you don't have to write anything else. This is giving you a faster way of doing that. It's saying row reduce and then just look, because this was something, I don't even care, something 2. We have rank 3 and then rank 2, and there's something wrong there. There's no solutions. Please subscribe right here, hit the notification bell. I'll see you next time we do homogeneous linear systems, and then we're done chapter 1.